Welcome back to Operating Systems Crashcast. I'm Victor, and today we're wrapping up Chapter 4 on threads with a comprehensive summary. Sheila, why don't you kick us off with a quick overview of what we've covered in this chapter?
Absolutely, Victor. In Chapter 4, we've delved deep into the world of threads, exploring how they differ from processes and why they're so crucial in modern operating systems. We've covered everything from the basics of multi-threading to more advanced concepts like multi-core programming and threading models.
That's right, Sheila. And for our listeners who might be preparing for interviews or just want to solidify their understanding, let's break down the key points. First and foremost, can you explain the fundamental difference between processes and threads?
Certainly. While processes are independent execution units with their own memory space, threads are lighter-weight units that exist within a process. Threads share the same memory space and resources of their parent process, which makes them more efficient for certain types of parallel processing.
Excellent explanation. Now, we've discussed various threading models throughout this chapter. Could you summarize the main ones for our listeners?
Of course, we primarily covered 3 multi-threading models: many-to-one, one-to-one, and many-to-many. In the many-to-one model, many user-level threads are mapped to a single kernel thread. The one-to-one model maps each user thread to a kernel thread, offering more concurrency. Finally, the many-to-many model multiplexes many user-level threads to a smaller or equal number of kernel threads, combining the best of both worlds.
That's a great overview, Sheila. Another crucial topic we covered was thread libraries. Can you highlight the main ones we discussed and their significance?
Absolutely. We explored 3 primary thread libraries: POSIX pthreads, Windows threads, and Java threads. Pthreads, which stands for Portable Operating System Interface Threads, is a standard for C programs, widely used in Unix-like systems. Windows threads are native to Windows operating systems, and Java threads are part of the Java language, offering platform-independent threading capabilities. These libraries provide developers with the tools to create and manage threads in their applications.
Excellent summary. Now let's talk about some of the more advanced concepts we covered. One that stands out is implicit threading. Can you explain what this is and why it's important?
Certainly. Implicit threading is an approach where the responsibility for thread creation and management is transferred from application developers to compilers and runtime libraries. We discussed several methods of implicit threading, including thread pools, fork-join frameworks, and OpenMP. These techniques aim to simplify parallel programming and improve application performance, especially on multi-core systems.
That's a great point, Sheila. Speaking of multi-core systems, can you briefly touch on the importance of multi-core programming in modern computing?
Absolutely, Victor. With multi-core processors becoming the norm, effective multi-core programming is crucial for maximizing system performance. It allows applications to take full advantage of available hardware resources by distributing tasks across multiple cores. This leads to improved responsiveness, faster execution times, and better overall system efficiency.
Excellent. Now, as we wrap up, let's discuss some of the key threading issues we covered. What are some challenges developers need to be aware of when working with threads?
Great question, Victor. Some of the main threading issues we explored include thread cancellation, signal handling, and thread local storage. Thread cancellation involves safely terminating a thread, which can be tricky to implement correctly. Signal handling in multi-threaded programs requires careful consideration to ensure signals are delivered to the appropriate threads. Lastly, thread local storage provides a way for each thread to have its own copy of data, which is crucial for maintaining thread safety in certain scenarios.
Thank you, Sheila. That's a comprehensive summary of the key points from Chapter 4. To our listeners, remember that understanding threads is crucial for modern operating system design and application development. The concepts we've covered here are not just theoretical, they have real-world implications in everything from mobile apps to large-scale server systems.
Absolutely, Victor. And for those preparing for interviews, make sure you can explain the differences between processes and threads, understand the various threading models, and are familiar with common threading libraries and issues. These topics often come up in technical interviews for operating systems and software development positions.
Great advice, Sheila. Well, that brings us to the end of our summary for Chapter 4 on threads. Thank you all for listening to Operating Systems Crashcast. In our next episode, we'll be diving into Chapter 5, which covers process synchronization. Until then, keep exploring the fascinating world of operating systems.